Okay, I'm Nikolay, and I'm going to talk about the open source anomaly detection system that we developed at Yahoo. I'm going to tell the high-level lessons that we learned. Oh.
The slide is full.
So, is that fine? Sorry?
It's actually the whole system.
Yeah. Oh.
Always works.
We really didn't need help to use up the extra time.
Okay. So I will talk about the open source anomaly detection system that we developed. I will tell the high-level lessons that we learned. I will talk a little bit about the models that we are using and talk about the experiments and the future work. So as most of you know, anomaly is something that deviates significantly from what is normal. And there are many types of the anomalies out there, and here's an example of one of them. Spatial anomalies, also called context-free anomalies. Also, we have the temporal anomalies, where the spikes or the level shifts can actually occur at any point in the sequence. And these are the types of anomalies that we are interested in. Because at Yahoo, we have millions of time series that monitor KPIs and system metrics, and clearly it is impractical to set the static threshold on each of them manually. And this has been the case for the past few years, unfortunately. Instead, we'd like to develop an automated system that automatically is able to detect anomalies on all of these metrics that we have, with high precision and high recall as well. So here's a simple anomaly detection algorithm that many people have used in the past. You can model your data as a multivariate Gaussian distribution, which has a density function parameterized by mu and sigma. And you can actually estimate your mu and sigma from the data that you have. So you can fit these parameters through the data, and then when you have a new data point, you can actually plug it into the density equation here and actually estimate how likely it is to actually observe that point. And given an epsilon, you can flag that point as an anomaly if it falls below the threshold that you set. So this approach works fairly well if your data is normally distributed or if you're looking for a particular type of an anomaly. In the anomaly detection literature, people have been addressing these issues all the way from neuroscience to statistics. However, what we have realized is that most of the anomaly detection models out there only deal with the particular use case that they are interested in. And at Yahoo, we have many different users that, for example, want to only detect spikes, or might only want to detect level shifts, right? Or might want to rank the anomalies in terms of how severe they are. So there was no way for us to, or at least it was very hard for us to come up with a single model that would actually answer all of these questions. And here is just an example of the types of time series that we are dealing with. As you can see, some of them are noisy, some of them are seasonal, some of them have spikes and the level shifts. And we'd like to design a system that is able to deal with all of these different metrics. So for this reason, we developed a framework, EGADS, which stands for Extendable Generic Anomaly Detection System. And it's essentially a framework that has a collection of all of these anomaly detection models. And it is largely unsupervised. It's composed of three main stages: the forecasting, anomaly detection, and the filtering. The filtering stage takes an optional user input together with some features that I'll explain later to filter out the anomalies that the person is likely not interested in. So let me dive a little deeper into the features that we are using. So we wanted to select the features such that they take big and small values whenever we have an anomaly. We actually separate the types of features into two parts, the time series features and the model features. So here are the list of time series features that we use. You can get a better glimpse of them in the paper, but some of them we derive from the classical time series literature, and some of them we developed actually ourselves. For example, we have the spikiness feature that talks about how sporadic the metric is, for example, or the flat spots feature, which just tells how flat the overall time series is. And here's just an example of the spectrum of these features for a sample metric. I know it's a little bit hard to see, but you can observe there's a big spike in the flat spots feature in this particular time series due to the fact that most of the time series is indeed flat. Also, we have model features which measure different deviations from the expected value. And we have absolute deviation as well as the percentage deviations. And here is an example of that. So the top time series is the original time series that we have. The second time series is the model, the model basically. And the next 5 time series are the model features. And as you can see, the absolute model feature, which is the 4th one from the top, has a big spike at the start, whereas the percentage-based model feature, which is the one here, has a big spike at the end over here. So we use both the time series features and the model features to do actually anomaly detection and to do filtering of the anomalies. So here's how the whole thing is deployed at a high level. So our framework is meant to be plugged into an existing data processing system, such as Hadoop or Spark, let's say. So the way that it typically works is that you have a batch processing stage where you build your anomaly detection and time series models. And during the storm, let's say, processing stage, the appropriate model is loaded into a memory, and then the data flows through it, and the anomaly is detected, and then it potentially filtered out based on the user feedback. So we have many. Sorry. So the model features are these ones here, basically. Yeah. So we have many forecasting models in the system. I'm not going to go through all of them. I'll just say that we have classical forecasting models as well as some of them that we actually developed. I will say one thing, that actually incrementally updating those models is very important for us, because we don't want to retrain them every single, let's say, a week or so. So we, for us, in order to be able to incrementally update those models, it was very important to convert them into a state space form like this, which most of you are familiar with, where you have a state equation that depends on the previous state, and you have an observation equation that depends on the current state. The problem with this is that the state equation does not take into account the observation that is new. So therefore, over time, your state equation will deviate more and more from what it's supposed to be. For this reason, we found that Kalman filtering correction of the state was extremely important for us. So with Kalman filtering, we can take the current state and we can take a new observation and actually correct the state to what it's actually supposed to be. We have also a lot of anomaly detection models out there, so that detect change points, spikes, so on and so forth. So you can look it up more in the paper. I will just talk a little bit about the one sort of novel model that we developed at Yahoo, where we rank the time series in terms of how misbehaving they are in the context of the current set of the metrics. So you are given, let's say, 1,000 metrics, and you're asked to show like the top 5 most misbehaving one in the set. So the way that we do this is that we actually extract the same features that I talked about before from those time series, and we extract the first 2 principal components from them, because we found that the first 2 principal components explain the majority of the variation. And then we can plot these 2 principal components on the 2D space like that, and use a simple convex hull anomaly detection approach to actually rank those time series by essentially stretching that band and ranking those time series in order in which they pop off as you stretch the band. So here's an example of how they would be ranked, let's say. And like I said, this is an extremely useful case within Yahoo, because you have service engineers who look at thousands and thousands of metric from a server farm, and instead of just focusing on each one individually, using this model, they can say, okay, show me the top 5 most misbehaving servers, I guess, in the farm. And that saves a lot of time. So for the feedback model, we use the generalized boosted regression model that, like I said, that takes a join between the time series features and the model features, as well as the optional user label. And then that's how the anomalies are filtered out. And like I said, it's a very easy and convenient way for the user to let our system know what types of anomalies are they willing to see and what types of anomalies they are not willing to see. So they can give feedback like this, or here's another screenshot of an email that we sent to some service engineers with some of the anomalies here. And once again, they can give us feedback here. And then we take that feedback with the features to, in the future, not show the anomalies that they don't want to see. So I will jump into the evaluation. We looked into the kappa and the accuracy statistics for the real and synthetic data set. I should mention that when we started this, there was no publicly available labeled anomaly detection data set. So we created one ourselves, and we've actually open sourced it. So you're more than welcome to check that out too. Here's how the data set looks like. You have your timestamp, you have your value, and then you have a set of features that I discussed. So for the forecasting results, I will just mention that there's always a trade-off between the training time and the memory usage. So we have use cases where training time is extremely important, not as much as the memory. For those use cases, we use models on the right side. And for the use cases where the memory is extremely important, but the training time is not, we use the models on the left side. For the anomaly detection experiments, I will just say that, so here we measure an F-score against the various time series sets that are actually open sourced. And so here I'll just say that out of there, we couldn't find a model that performs the best across all of these sets. So that was the main motivation for our work, is to not just focus on a single model, but to create an ecosystem, so to speak, or a framework where users can plug and play their own model to handle the use case. And this is some of the filtering module experiments where we measure the kappa and the accuracy statistics as the depth of the tree and the number of the tree increases. And here is the distribution of those statistics once again, and they all range about 0.9 or so. And here also the raw true positive rates and the true negative rates for the feedback model. Also, we ranked an importance of the features for the Yahoo Mail use case. And we found that the level shift feature and the model score feature were the top 2 most important features for the feedback model. So for the future work, I will say that the model selection continues to be an extremely important project for us because currently we have to try every single model, and then we have to pick the one that actually maximizes the statistic that we're interested in. But our intuition is that the time series features and the model features that we have can actually let us know from the beginning which model we need to use. Incremental model updates are also very important. Multivariate forecasting and anomaly detection is also very important. And also, as we increase the number of users that we have that are using the system, simplifying the deployment of the system also becomes important. So here I will stop. I just want to say that actual open source, all of the things that I talked about are actually open sourced. So we welcome contributions from you guys, and I'll take any questions. Thank you.
Microphone's coming for
I've got a lot of questions. Let's try to limit to two. First of all, have you tested, have any of the models have any of the other outlier detection methods that you've tested against, have any of those been specifically designed for anomaly detection in data centers or not just general time series?
So, I mean, all of the models that we have tested detect a certain type of anomaly. So, for example, for the data set that has spiky anomalies, we only use the models that detect spikes.
I mean, specifically for the job of anomaly detection in the data center.
So, in the data center, well, actually, our anomaly detection is not only used in the data center. It's also used for the front facing user applications too.
Yeah. Okay. And the second question is, how do you deal with variance in the machines that run this? The server in the server farm may not actually be uniform hardware.
Okay.
And that means that you do get outliers, but they don't mean anything.
Very good. So that's where the anomaly detection model that I discussed, the one that ranks the anomalies, that one would be very, very important for your use case, because there, you're right. If you do a univariate anomaly detection on every single metric, then you'll have a lot of anomalies, right? Mm-hmm. But if you rank the anomalies with respect to the other servers, then you're not going to get the false positives.
Are any of the other anomaly detection multivariate?
There are some, but we haven't actually tried them yet.
Microphone's coming.
Thank you for the talk. Do you have any suggestion about how Yahoo is encouraging to use this kind of system in real operation? Like, I have many industrial experience about anomaly detection, but in most of the case, users don't want to use that system because of many false positives at the beginning. And your system has a feedback loop. And I think if time goes by, maybe your system false positive rate is decreasing. But how that initiation phase you can let Yahoo use, operate the other users to use your system?
Well, I mean, our system actually automatically trains the appropriate threshold for the model, okay? So that way the false positives and the false negatives are minimized.
But I think the transaction, let's say billions of transactions, yeah. Even if the false positive rate is 0.001, the number of false positive is still 10K or
So I mean, that's where the feedback model also comes in, right? So based on your feedback and on the features, we can actually fine tune the model to not show you the anomalies that you actually wouldn't want to see. But just to make it clear,
statistics like how long do you need to get the practical false positive rate using that kind of
it depends on many factors, such as what type of anomaly that you want to see, what type of time series you have. Is it noisy, cyclical, fairly stable, so on and so forth.
Okay, thank you.
Do you see the need to distinguish between anomalous system response and anomalous usage? For example, traffic increases, perhaps response time increases, and there's a normal way it increases. So that's probably not an anomaly, but traffic increases and response times goes up more than expected.
Right.
Do you have to distinguish between anomalous usage and anomalous behavior?
Yeah, so that's where the multivariate anomaly detection actually comes into play. So that's the exactly thing that we are working on at the moment, where, like you said, we monitor the usage as well as the latency, right? And if both of them go up, then it's okay. But if one of them goes up and the other one negatively is impacted, then it's an anomaly. Okay. Right. Right. Thank you. Thanks.
Thank you.
Thanks.